Okay, so I think this was a good discussion, and hopefully this got you all thinking a little bit about some of the pieces that we are going to talk about next. So which is basically evaluating model interpretations and explanations, right? Okay, so let's kind of think about this first at a very high level, right? So whenever we have some model interpretations or explanations, so we want to evaluate two pieces. The first one is the meaningfulness or the correctness of explanations or interpretations, right? And the second one is the interpretability of these interpretations or explanations, right? So both are important. So as I think several of you brought up, if I give you an explanation that's actually not being used by the model in a very specific way, or it's an incorrect description of what the model is actually doing, that's very bad and harmful actually, because now we are telling people that this is what the model is doing, and that's not what it is doing. That's probably worse than not giving them anything, right? And the second thing is, you can give people something, but they need to be able to look at it and make sense of what that is, right? If it is too complicated, if I give you 200 million parameters, that's not going to be useful, even if it's a very accurate representation of what the model is doing, okay? So let's talk a little bit about evaluating interpretability. So these are two pieces: evaluating the correctness or meaningfulness, and then evaluating interpretability, right? So when it comes to evaluating interpretability, so here are three classes of evaluation that was suggested in one of the prior survey papers. So the first is functionally grounded evaluation, where you use some kinds of quantitative proxy metrics. There are no real humans doing anything with it, but you use some proxy metrics to determine the interpretability of a given interpretation or explanation, right? The second is human grounded evaluation, where there are people, but they are doing simpler tasks and not the exact tasks that are done in an application. Okay? And then there is application grounded evaluation, which basically is what you guys were pointing out, which is just sort of do as close to possible to downstream tasks, right? So let users do either the exact downstream task or something very close to it, and then see how much they're able to do it. So all of these can help with evaluating the interpretability, or probably more broadly utility of these interpretations and explanations, right? So just to give some examples of each of these, functionally grounded evaluation, the proxy metrics could be something like number of rules or number of prototypes, right? Just lower is better. So we are not doing any user studies, we are not doing any kind of human subject evaluations here. We are just saying less things are better, right? So that's just a rule of thumb, by the way. And human grounded means you can think of like 2 to 3 different kinds of tasks here. No, recall that this is basically a simplified version of human evaluation, right? So either we force people to make a choice. So I give you 2 explanations and then I say which one is more easier for you to read, right? So we force people to make a choice, and through that evaluate the interpretability of these explanations or interpretations. The second one is forward simulation or prediction, which means I give you the input, the explanation, and then the output, the input and the explanation, and I ask you to predict the output of the model, right? So you should look at the input and the explanation and say, oh, I know that the model, or at least I can infer that the model can predict a label 1 for this instance, right? And the last one is counterfactual simulation. In that case, I'll give you the input data point and then the explanation, and people should be able to tell what features need to be changed in order for the prediction to change. Of course, this is probably more obvious with some explanations than others, but that's another sort of like a proxy task that is used to evaluate interpretability, right? So last one, of course, is either let domain experts do the exact application task, or let domain experts do a simpler version of the application. But in either case, we are testing with real users to see what is going on, right? Okay. All right. So let's talk a little bit first about evaluating the inherently interpretable models. So here, just kind of, sort of instantiating it for this setup, we want to evaluate the accuracy of the resulting model, because these models are, at the end of the day, classifiers or predictors, right? So when evaluating inherently interpretable models, you want to see what's the accuracy of the resulting model. You also want to evaluate the interpretability of the resulting models, like for example, prototypes. So we get those as interpretations. We want to see how understandable they are, or even attention weights. And the last thing is, in this case, and I think some of you have probably answered this question partly or indirectly. So in this case, do we need to evaluate the correctness or meaningfulness of the resulting interpretations? What do you guys think? So it's an inherently interpretable model, right? So since it's a model, you're evaluating its accuracy. Since it gives you prototypes or weights, you're saying how interpretable are these. But do I need to evaluate the correctness of those prototypes, or, say the meaningfulness of those prototypes or attention weights? Or is it obvious, like since it's coming from the model, it must be right? Or are there some cases where it is obvious and some cases where it's not, because there is a whole gamut of inherently interpretable models? Yeah?
I mean, if these are things that you do to your model to hopefully make it interpretable, then you need, in the end, to actually evaluate it.
Right.
But if you actually believe that this is exactly interpretable, then...
Right. So if you're adding layers, you might want to check the output of what those layers are producing. That's what you're saying. So what do you think about, like in the very beginning, we talked about some rule lists and rule sets. What do you think about those? Do those need some kind of correctness evaluation for the interpretation?
Correctness is probably fine, but like meaningful, I guess, yeah.
But what exactly you mean by correctness?
Right. So when I say correctness, for example, if I give you a prototype output by the prototype layer in the models that we were considering in the deep nets, so should I just assume that, oh, I've added a layer, the model is giving me a prototype, apparently it's basing its prediction on this prototype. And should I just accept that at face value, or should I need to probe that a bit more?
I think you should probe it, because
Right.
who knows what it gives, right?
Right. But would this answer change if we were talking about, say, a rule list? Maybe, okay.
So when you talk about rule list, you mean like a global
Yeah. Just not even a post-hoc explanation. Like just the rule list is the classifier.
I don't know. I think that if rule list is the classifier, it's all information that you. This is how you do it.
Yeah.
It's all there.
Yeah.
Either you doubt your model or you believe the model, and then it's all there.
Right. Yeah. Right. So in some sense, for some of the very initial models we talked about, everything is all there, right? Like as she's suggesting. So you essentially, the 5 rules you have in your hand are the model. So that's what is used for classification. So maybe in that setting, this whole notion of evaluating the correctness of the interpretation is not really as relevant or important. But the moment we go to something like adding layers to the models, you might want to double check what those layers are learning, and if they're even learning something useful or meaningful, right? And we'll talk a little bit about how some of the prior works have thought about this particular part, but hopefully the rest too are like pretty obvious, which is accuracy of the entire model and interpretability of these interpretations. Okay. So yeah, I think we did some of this discussion already about this. So essentially, my plan was to sort of go over some of these and then say, how do we think about like evaluating the accuracy or the interpretability of this? So maybe we can do a couple of these, and then I think we have discussed the third point at length, which is correctness. So I think in this case, the correctness of the interpretation is not really something that we may question much, because this is essentially the model, right? It is what it is. Again, whether it's causal or not, it's probably not, but like we are not getting into that, right? So accuracy of this model, I guess you can use this to compute the labels for your test points, right? and then get accuracy numbers of this model, and accuracy is what it is, right? So I guess interpretability, how about evaluating interpretability on this? Would like number of rules and like, you know, the downstream applications and some of those things still hold here, like asking people to do predictions based on this? Do all of those seem like valid approaches to test the interpretability? Yeah, that's right. Okay. I think we can argue something similar for this also, right? So it's essentially a slightly different form of classification. So that is that, okay? So one thing I wanted to show you here is basically some kind of comparative analysis between the rule lists and then the decision sets, right? So while these are almost seeming like very similar models, or at least in the constructs that they use, they seem very similar, they can impact certain tasks that we might ask people to do, right? So one way to think about this is we can just compare the number of rules and predicates in these models and say whichever is lower is better, right? The other thing is, as we were all discussing, let's do some user studies, okay? So one of the user studies that was done, and what we did here was basically get a bunch of users, and each user will be randomly assigned to one of the two models, either the rule lists or the decision sets, and each of them will answer about 12 questions, 10 objective and then 2 descriptive questions. So the objective questions look something like this. So essentially we say there is a patient with the following medical record. So we have partial information about this patient. Just using this partial information, can you be absolutely sure that the above model will say that the patient suffers from lung cancer, right? So questions like these are the objective questions that we were asking. So essentially give partial information and see if people can, you know, correctly ascribe the prediction of that model, you know, to basically the point that we are thinking about. And the next one is a descriptive question where we say, so write a short paragraph describing the characteristics of asthma patients based on these rules provided above, right? So they have to just describe in plain English what are the characteristics of asthma patient according to the rules given. So what we observe is actually something interesting for these two specific tasks, right? So we have seen that this kind of unordered rules are actually helping people give answers to those questions that we are asking much more accurately and in a much more faster way, both the objective as well as the descriptive questions. So in some sense, even something as small as having an else if structure which requires you to unroll the previous rules and then say, oh, if that does not apply and then I come here, that logic is already cognitively taxing to people in doing certain tasks, right? Like in the kinds of questions that we were asking. So that kind of shows that even simple changes to visualizations or constructs can have a big impact when you think about downstream tasks or interpretability, okay? All right, so let's talk about this prototype and attention layers, I think, which we already kicked off. So I think several of you are thinking that there is no guarantee that these prototypes and attention weights are going to be meaningful. So what do we do about it, right? So one of the prior works by Jain and Wallace, they actually check if attention weights correlate with other measures of feature importance, for example, gradients. And they also check if we were to give different attention weights, would they yield in different predictions? So they do two kinds of checks to determine the correctness or meaningfulness of these attention weights, okay? And the answer turns out to be no in both cases. So neither are these attention weights learned by the attention layers of the model correlating with the gradients of the model with respect to input points, nor is changing the attention weights to different values changing prediction significantly. So this paper basically raised a lot of questions about this whole notion of let's add some layers and make models inherently interpretable and then everything will get solved, right? Because the complexity of these models is such that I think the way people are just combining different things, adding a layer and saying this will take care of everything, that's unfortunately not turning out to be true, right? Okay. So let's talk a little bit about evaluating post hoc explanations, right? And under this category, so you could think of several aspects that can be quantitatively evaluated and some aspects that have to be qualitatively evaluated or through user studies, right? So first is, of course, evaluating the faithfulness or correctness of post hoc explanations, and we'll discuss that in detail. Next is evaluating the stability of post hoc explanations, which is when you make small input perturbations, how much do the explanations change, right? Third is evaluating the fairness of post hoc explanations, which means is the accuracy of explanations kind of roughly similar for majority and minority groups, right? Or are the explanations, for instances, in a majority group much more accurate than the explanations, for instances, in minority group? If so, there is some weird kind of unfairness or bias that is kicking in there, right? And lastly, evaluating the interpretability of the post hoc explanations, okay? So let's go piece by piece, and this is actually like this entire sort of setup of all these evaluations is part of one of our recent benchmark papers, which I'll also discuss a little bit at the end of this note. Okay, so evaluating faithfulness of post hoc explanations, again, there are different ways to do it depending on the kind of information you have available, right? So for example, let's say that you have some ground truth information available, and that ground truth could come in the form of, here are the top K features or that the model is using when making these kinds of predictions, and I know for a fact that those are the features the model is using, right? If such a ground truth exists, then you could basically think of several sort of agreement metrics in the top K features, and also generally if you're able to rank features in some order of importance, you can use that ground truth to sort of determine how accurate your different kinds of explanations are, right? So for example, you can think of this as feature agreement, which is the fraction of the top K features output by your explanation, how many of those actually appear in the top K features of the ground truth, right? Or you can say rank agreement, not only should these features that are appearing in the top K of explanation appear in the ground truth, but the rank ordering of these features should also match the ground truth. Then I consider it as there is a rank agreement, right? And you can make them stricter. Like for example, sign agreement could be that the sign, whether it's a positive contribution or a negative, even within the top 5 features or top K features, that should match. Sign rank agreement, basically the sign should match, rank should match, the features should appear, everything happens, then it's a perfect match, right? So you could think of like a bunch of these kinds of things, or you could also think of rank correlation coefficients. If you are given a ground truth ordering of features somehow, if you're given your explanation ordering of features, then you can compute rank correlation coefficients. You could even compute pairwise rank agreement, which is basically take 2 features at a time and then see if the ordering of those 2 features is maintained between the explanation learned and a ground truth explanation, right? So these are all the things that you can do if there is some notion of ground truth and some notion of ordering among the features in that ground truth. Okay. Is there a question? Yeah.
So does this not run into the same problem that we discussed earlier, that are we evaluating the correctness, or are we evaluating how good our explanation is, or are we testing how good our model was, and then whether my essentially I could have had a bad model but a good explanation on top of it,
Right.
but that explanation would fail these tests because the model itself did not pick up the correct.
Right. So let me clarify the notion of ground truth here, right? So when I'm using the term ground truth here, I don't mean it's a ground truth associated with the data. I mean it's the ground truth associated with the model, right? For example, if your underlying model is a logistic regression, you know the answer for what are the top K features of that model, right? So you take that and that is your ground truth. So so this ground truth should not be confused with the ground truth of the data. This is the ground truth of the model. If we know the ground truth of the model, then we can apply these metrics.
But wasn't the whole point to find out the ground truth? Like, how do I find out the ground truth for more complex models which are not linear?
Yeah, so this is basically the case where your models are simple and you're able to do this, right? So we are going to come to different, we are going to relax that assumption, right? So this is a very basic case. Wherever you have ground truth available of the model, we can potentially use this. In fact, in one of our papers, I don't think we have too much discussion in this about it, but we can create synthetic data sets which sort of create these islands of data points that are farther away and fit a linear model on each island. So we know for a fact that there is one linear model operating on this island of data points, and that will give you the ground truth feature importances for that island. And we have some theorems and conditions that need to be satisfied, and any accurate model that you train on these synthetic data sets will have to respect these feature importances across these islands, right? But this is only possible because we are able to generate synthetic data sets. Yeah, okay. All right, so now we are going to the next condition where we don't have ground truth, but our explanations themselves are models, right? So for example, Lime is basically fitting a linear model on some local neighborhood, right? So if the explanation itself is a model, we can basically take the explanation model and then get predictions of that model on instances in the local neighborhood, and we can compare how these predictions match with the predictions of the underlying model, right? So you have one model, which is your explanation model, you have one model, which is the underlying model. Compare what fraction of the predictions of these two models match in a given local neighborhood, right? And the higher the match, basically the more accurate the explanation. That's one notion of thinking about faithfulness when your explanations themselves are models, okay? So now the question is, what if we don't have any ground truth, right? And what if explanations that we are looking at cannot be considered as models that output predictions, okay? So for that, we have again some tricks. So one of the basic idea here is remove important features as designated by the explanation and see what happens, right? So for example, here is an image, and we have constructed some explanations on this. And according to the explanations, there are a bunch of important features. Keep removing those from that image, right? So keep removing the important features one after the other from the image and see how the prediction probability drops, okay? And in some sense, if removing the top 5 important features from the image as given by an explanation causes a bigger drop in the prediction probability than some other explanation's top 5 features, the first one is better because those important features are somehow capturing more of the predictive power, right? So that's the idea essentially. Okay? Yeah?
What do you mean by like removing? So if you if you change the color,
Yep.
it becomes a different picture rather than like you don't really remove, right?
Yeah. So in some sense, this is where the notion of background distribution comes into picture. So often for each data set, people basically have, and this can be selected either through pursuing data or like looking at data or using some computational methods as well. But essentially you kind of come up with, in this data set, given the nature of images, maybe replacing something by black means I'm removing that feature, quote unquote, right? So that's one way to think about it. The other way to think about it, if such a notion of background distribution is not coming out naturally, is perturb the values of those pixels. So you have some values, RGB values, just add a bunch of noise to them, okay? And when you add that noise, your prediction should change if those features are important, right? Yep.
So do you think that the way how you delete pixel will influence outcome of this experiment?
It depends on, so typically as I was saying, so think of it as for each data set, there could be some background image which basically is like a no signal image, right? So if we are able to get to that, then you are truly removing a feature. Otherwise, you are merely changing something you have there to something else. But the idea is still the same. If a feature is important and if you mess with it, the prediction should change drastically, right? Okay, so that's one piece of it. And then the other piece of it is, insertion or like adding important features and seeing what happens, right? So for example, if this is the background image, so then essentially you keep adding features and then seeing how much sort of the prediction probability changes, right? In some sense, I would think of it as there are two sides to it, right? So take important features, perturb them, and if you're perturbing important features really, your predictions should change. The alternative is take unimportant features, perturb them. If your prediction is changing, then that's bad because your unimportant features are carrying signal, right? So those are roughly the two ways of thinking about how to evaluate the faithfulness of explanations. But when doing this evaluation, I think it's useful to think of it as a comparative one, right? So I don't know if it's absolutely good if I get some value of drop in probability, but if there are two explanations where one has a higher drop in probability than other when I'm removing important features or perturbing them, then this explanation is better than the other, right? So it at least helps you place explanations relatively in terms of their faithfulness, okay? All right, so the next aspect is stability. So are post hoc explanations stable with respect to small input perturbations, right? So to this end, like this was one of the first metrics proposed, and the idea or what's going on here is that you are computing the maximum change in explanation relative to the change in the instances. So if you take an instance xi, perturb it a bit and do this like several times, and then you calculate the maximum change in the explanation divided by the change in the points or the distance between the points. So then you will basically get a value for what is the maximum possible change in explanation in a given small epsilon ball neighborhood, right? So the higher this value, the more unstable the corresponding explanation is considered, okay? So that's one part, that's a metric. So now there are a bunch of other questions that sort of come out here, right? So what if the underlying model itself is unstable? In the sense that if I make a small perturbation to the point, the prediction of the model itself changes, then in that case my explanation should change, right? Like it's just reflecting model behavior. So to account for that, there are a couple more metrics in some of our recent works. One is you also account in the denominator for the change in the output prediction probabilities, or you in fact account for the changes in the intermediate representations of the model as you sort of perturb instances, right? And the change in your explanation should be proportionate to some of these changes, and that's when it is sort of considered stable because you're also accounting for the model's properties in there, okay? All right, so fairness of post hoc explanations. So really, fairness of post hoc explanations is about taking all your faithfulness metrics, stability metrics, and computing the mean values of those metrics for a majority group by averaging all those metrics on instances in the majority group and the minority group, and seeing if the two means are different in a statistically significant way, right? If there is a difference, then there is potentially unfairness because, for example, think of a healthcare situation where there are a bunch of explanations for men and a bunch of explanations for women about how they are getting diagnosed with a disease, right? If the women's explanations are looking correct but are actually incorrect, they are not faithful, the doctor might just rely on them and make decisions according to those and have no idea that, those explanations are in fact incorrect, whereas one group's explanations are correct, right? So it can cause all kinds of issues in practice. So this is also undesirable in some sense. So your accuracies across different subgroups that you care about with respect to explanations should not be significantly different, okay? So why and when can such unfairness occur? Or, you don't have to give all the sort of sufficient conditions, but any intuition about when such unfairness can occur? So when can explanations be more accurate for, let's say, male subgroup and less accurate for female subgroup? When does that happen? on the one subgroup, you mean wherever there's, I think you're sort of in the ballpark. So lack of data about one subgroup. Any other thoughts? Okay. So how about we think of this scenario? So for example, let's say we are using Lime, right? So what is Lime doing? Lime is trying to fit a local linear model at each point, which is explaining its prediction, right? So now, when is that local linear model more accurate for one group than the other, right? So maybe the underlying model is actually a linear model for instances in one subgroup, and it's actually a non-linear model for instances in the other subgroup, right? So potentially the differences in the model surface and the ability of your explanation methods to capture those model surfaces can cause this unfairness, right? So it's really, it's not a big devil in there. It's the fact that you are trying to fit a linear model. Now your underlying model is linear in some parts of the feature space and is non-linear in other parts. So you're just getting a better fit in some parts than the other, right? So that's when unfairness can happen, but it's important to be mindful of something like this because it can affect how correct your explanations are. Okay, all right. So this is something that we have just looked at earlier, just kind of bringing that back into the foreground because we are going to talk about interpretability and how to evaluate it for post-hoc explanations, okay? So the first one is essentially forward simulation. So essentially you will show a new data point to the user. The user may also have access to past predictions and explanations. But for this new data point, you basically show the explanation to the user, and then you are trying to make the user guess the prediction of the model based on this instance and its explanation, and you will compare the accuracy of the user, or rather you'll compare the label assigned to the instance by the user with that of the label assigned by the model, right? So if those both match, then the user is accurate or they're able to simulate the model, okay? So this was something that was done in one of the studies by Microsoft Research. So essentially they showed people instances, their corresponding explanations, and tried to ask them questions like, what do you think this model will predict? How confident are you that the model will predict this, and so on, right? So these are the kinds of tasks that people typically do in this setting, right? Or there is even more sort of like, the next level of tasks in terms of complexity, where you will check for the effectiveness of human AI collaboration, right? So again, as some of you were pointing out, downstream applications. Are these explanations useful for making decisions, right? Where algorithms are not by themselves reliable. So for example, there are some studies which basically do this with tasks like deception detection, which is identifying fake reviews online. So if you give explanations to humans as they are identifying fake reviews online, will it help, right? So that was the kind of task that was done. And yeah, so the results in some of these tasks are actually positive. For this particular task, people did find, or researchers did find, that with explanations, humans were able to identify fake reviews online much better than without. Okay. So this is one of our recent studies, and this has been in the making for a long time because it involves access to doctors and people who are actually domain experts in healthcare. So what we were doing was we were trying to work with the setting of a prediction problem where we ask a bunch of doctors a prediction question, which is, I'll give you the patient's current health record in terms of their current symptoms, their previous medical history, family medical history, all of that stuff. And you have to predict if this patient is likely to be diagnosed with breast cancer within the next 2 years. Right? So this is not a diagnosis problem, it's a forecasting problem, right? So we basically carried out studies with about 78 doctors who are residents in internal medicine in hospitals in Boston. And each doctor, so this is an online user study, each doctor looks at 10 patient records from historical data and make predictions on them, right? So none of this is live. We are just kind of mocking the situation that they might, encounter in their practice, but we are doing this with historical data, okay? So what we found was something interesting. So if we let just doctors make this prediction on their own with in fact no models, their accuracy of predicting somebody's chances of getting breast cancer accurately is about 78%, right? If we give them the prediction of the model, so instead of just the doctor, we say, okay, for that individual, it's a label of at risk with a probability of 0.91. Okay, so if we give that much, just that part, and the model's accuracy in this case is about 89%, what we found was something very interesting. The combined accuracy of the doctor along with model predictions is actually worse than the model's accuracy. And I'll talk a little bit about why, but I think that's not the central point of this discussion. But then there was a third condition where there was a doctor. We showed the prediction probability, and also the top 4 important features that went into the prediction, where we evaluated the faithfulness of these and picked the method that was giving the highest faithfulness according to this perturb important and unimportant features matrix. Okay, so in that case, the accuracy shot up quite a bit. So we are trying to do this study on a bit larger scale, but essentially this is with real doctors, but a task that is close enough to their day-to-day decision making, right? So that's one thing that I wanted to point about. And the reason why that could happen is potentially there are also instances where people are seeing that the important features are things like those: appointment time, day, zip code, some of these spurious features, and in those cases, doctors are able to say, I don't want to rely on the model prediction, make my own decision, right? Okay, yeah.
Yeah, so did you try to kind of have a control experiment where you have your doctor and the neural network output, but you tell a lie, like not what the neural network said, you put a random number and see what the doctors would guess.
Yeah, so what we did was, we did not do that with the models or predictions, but we did it with explanations. So what if we could just randomly pick top 4 features and give it to the doctor? Would that actually help improve their decision making? Is it just the concept of explanation, or is it a correct explanation? And turns out it is the correct explanation. In fact, what we have seen is if I just pick randomly top 4 features and say, here is explanation, and if doctors look at it and make decisions based on that, their performance is kind of much worse than what they would. Sometimes I think we are trying to replicate this across different hospitals, but at least in one hospital, it's actually worse than what it would have been had they just have access to nothing at all. So bad explanations are going to hurt very badly. So that's the moral of that story.
Yeah. So whenever I see the first two, my gut feelings whenever the doctors are unsure about something, they tend to trust the neural network. So basically, they tend to trust the science, the computer science.
Right. Well, I think that should depend on whether the model itself is sure about the prediction or what it is doing also, right? But yeah, that's a good point. Yeah.
In the last row, you said that you're giving an explanation about important features, but they're not actually important features.
Not in this set. None of these numbers are with the bad explanations or randomly chosen explanations.
Oh, so the accuracy of 93%. Okay.
No, it's not. It's only the accurate explanations. Yeah. Okay. So yeah, these were just clarifications of how those numbers are coming in. Okay. So let's kind of zoom out a bit, and several of you have already mentioned challenges of that evaluating these kinds of interpretations or explanations is challenging. So why? Because first of all, this is actually an ongoing endeavor, and what are the challenges associated with that? One thing that needs to be kept in mind is parameter settings or hyperparameters influence the resulting interpretations or explanations, right? So given that, we need to be very careful about those settings and what we are using, because, for example, in line, while we do not look at the objective per se, so the objective function has 2 terms. So one of it is, it's basically trying to fit a linear model that matches the predictions of the underlying model. The second term is a regularizer term, where it is trying to reduce the number of features for which the coefficient weights are non-zero, right? So essentially, depending on the trade-off parameter you set there, you might get different answers. Or essentially, even if you change the number of perturbations, you might get different answers, right? So there are all these things that need to be kept in mind when thinking about, the explanations that are being generated. Okay, so one approach can generate different explanations depending on the parameter settings you are producing or providing, right? And the second thing is, as we have seen, there is a whole lot of diversity in terms of what is a basic unit of interpretation, what is a method doing. For example, there are a bunch of methods, all of which produce feature importances, like Lime, SHAP, Maple, gradient-based methods, all of those, they're giving you some numbers indicating the importance of features, right? But they're all using seemingly diverse approaches to do that. Like one is fitting a linear model, one is trying to get to shapely values, one is trying to compute gradients, the other is trying to smooth gradients. So they are all doing like a lot of different kinds of things, right? So given this diversity in approaches and the constructs, like how do we even think about comparisons? So we have to come up with diverse metrics, which is also non-trivial. And user studies can themselves be inconsistent because they're often affected by the choice of UI, phrasing, visualization, the population that you're considering, if you're giving any incentives to people to do these tasks and so on, right? So there are all these things to be kept in mind, which is why some of the results that we discuss, and I do talk about like why we are getting like mixed conclusions about the utility or interpretability of some of these methods, is because of this, since it is still an ongoing active area of research and things are still being figured out, right? Okay. So I want to kind of just talk a little bit about some of the currently available open source tool for quantitative evaluation. So none of these are for user studies. So these are just quantitative evaluations. If you're thinking about inherently interpretable models, so there is this Interpretml, GitHub repo and also online library, which can be useful with a bunch of inherently interpretable models, including GAMs and rule lists and sets and all of that. So then there are a bunch of XAI libraries for different things. For example, Captum from Facebook has a lot of implementations of different post hoc explanation methods. Then there are some of the benchmarks, like Eraser is a good benchmark for explanations on NLP. So we have this library called OpenXAI, which is basically like 22 metrics, all the things that we discussed, state-of-the-art metrics. We are also having some public dashboards for comparing, explanation methods on different kinds of data sets and so on. So it's pretty easy to use some of these frameworks. Actually, both OpenXAI and Qantas, you can use with 11 lines of code, you'll be able to evaluate different explanation methods that are supported by these packages, right? So things are getting there, but whether we have correct answers, conclusive insights and inferences, that's another question. I think that's going to take some time. Okay, all right. So we have actually a bit more time. So I'm going to jump into the next part, which is trying to sort of think about the insights that we have about the behavior of different inherently interpretable models and post hoc explanation methods. Okay? All right. Any questions so far? Sorry, maybe I'll pause here and see. Yeah?
So, let's say we have an image or something. If we use different explanation methods, very often we get very different results. How do we?
Great question. So your question is, if we use different explanation methods, if I get different results, what do I do, right? That's a great question. We are going to touch upon that quite a bit in this part. Okay? Yeah. All right. Yes.
So we get different results doesn't necessarily mean that it's bad. Even if you use one particular say line, and we should get different results because we can have multiple explanations for the same thing, right?
So you're saying different methods are giving different answers, that does not have to be bad.
Yeah, even from the same method. Say if you use
same method, okay.
Say different or same. Say for instance, we use line.
Yep.
And we use different perturbations, and we get different explanations.
Yep.
That does not mean that line is bad or anything, because we can have multiple explanations.
Right. So your question is, even if I just use Lime and if I just set the number of perturbations to different values, If lime gives different explanations, why is that bad, right? So we'll get to that in a bit. So there is something fuzzy about this particular aspect. If I set the number of perturbations to different values, if I'm getting different explanations, the most likely answer is the explanation method has not converged to an expected explanation. So how do we think about that? Of course, if you change the parameters, like for example, the lambda which balances the regularization term with the loss term and so on, then you can get different explanations, right? So one is, having less non-zero coefficient associated with features, the other is more accurate in terms of the model it is fitting and so on. But we'll get to this discussion. This is exactly what is the next part, okay? All right, okay. So let's get into this. So there is a lot of recent focus on analyzing the behavior of post hoc explanation methods. And there are a bunch of empirical studies analyzing the faithfulness and stability, fairness, adversarial vulnerabilities, utility of post hoc explanation methods. And a lot of these studies also demonstrate the limitations of existing post hoc explanation methods, right? So this is a very active area of research. Personally, this kind of empirical and theoretical analysis is something that I'm very keen on and constitutes a bunch of our current work, and we'll talk about some of the theoretical results and empirical results and so on. Okay. So this is actually a paper by Julius Adebayo et al. In 2018. What they were trying to test is basically they were trying to see if gradient-based explanations are any good, which is basically, input gradient, input times gradient, smooth grad, integrated grad, all the things that we were talking about. So they were checking if those explanations are any good. And the test that they did was that they started randomizing the parameters of the model of deep neural networks, starting all the way from the top layer, that is closer to the softmax layer, and all the way till the bottom layer, okay? So as they randomized each layer, what they realized is that the explanations are not really changing with these methods. Especially a couple of them, I think, even gradient times input has that problem, but it's more pronounced with some of the other methods, which basically means no matter what the parameters on your network are, somehow these methods are trying to give you the same answer. And that is particularly happening with some of these methods because I think some of you were already pointing to your discussion there. So some of these methods are trying to guide or bias the explanations generated to something that is likely to be intuitive to the users, right? Because a lot of times people are oh, we should get an explanation that's less noisy, that's more meaningful. All that is amazing, but it's only amazing when your model is also doing that, right? But if your model is not doing it and you're sort of guiding your explanations to do it, then you will have beautiful explanations for a model that's bad, right? So that's what is kind of happening with some of these approaches. So basically they're failing the model parameter randomization test, okay? And the next thing that they tried is that they basically randomized the class labels of instances. So they took the data set, they randomized the class labels of the instances and had a different model, and even that really did not impact the explanations, right? So this is bad. So basically changes in model are not being reflected in the changes in explanation at all, right? For some methods more than others, right? Mostly those guided sort of methods that are being used. Okay, so we talked a little bit about stability. We asked the question, or at least we saw this metric earlier, and we were thinking if post hoc explanations are unstable with respect to small non-adversarial input perturbations. Turns out approaches like lime can be unstable. So these approaches are relying on perturbation-based perturbations. Basically, they create perturbations of an instance and try to fit a model on those. So they are more likely to be unstable than some of the other gradient-based methods. So that's one of the finding in one of the studies. And this is true even when the underlying model, whether it's prediction or whether it is representations, those are not changing much. So even when they're not changing much, the explanation is changing drastically with some of these methods, for example, lime. So there is, I think one of you raised the question just now about, different explanations coming out from the same method, right? So I just want to highlight this example a bit, and this is one of our works a couple of years back, is that, so what we see in this image, maybe I'll focus on the last two pictures. So the underlying model is a nonlinear model, and in figure C, the number of perturbations is high, and in figure D, the number of perturbations is low. So when the number of perturbations is high, and if I keep repeatedly rerunning line with the same number of perturbations, I get kind of similar answers in terms of explanation, okay? But when the number of perturbations is low, and if I keep rerunning line on the same point with the same parameters, I get varied answers in terms of the explanations that Lime outputs, right? So indicating the potential that, with fewer samples or fewer perturbations, the method has potentially not converged, so there is effect on the perturbations you pick on the explanation that you get, right? Whereas if you increase that number, this chance reduces and you are likely to get similar explanations, right? So that's one possible way to think about it. But I think the point that I'm trying to make is that we need to be very careful about setting the parameters in these methods, because these kinds of issues can happen, right? Okay. So here what this is sort of bringing up is an important question, which is, okay, so maybe there's a problem with having too few perturbations, right? So then the question is, what is the optimal number of perturbations? Okay, so that is some of the recent research which I'll touch upon as we are thinking about some of the future directions. Okay, all right, so some are findings, right? So some of the recent works also identified that post hoc explanations can be easily manipulated. So just to show you an example, so here is the original image, here is the explanation generated. Here is the manipulated image. You kind of changed it very slightly in an almost imperceptible way for a human eye. And this is the explanation. Right? So in some sense, for those of you familiar with adversarial examples literature for generic machine learning models, this is analogous to that in the explanation literature, right? So essentially this paper and also the next paper, they're trying to do something very similar. What they're trying to do is find the smallest perturbation to the input image that can help maximally change the explanation, and also kind of anchor it to some misleading explanations that an adversary would want the approach to generate, right? So that's possible, that is doable. Of course, whether adversaries will have that kind of access in practice or not, that's a separate issue, but you can, if you were an adversary with a lot of control and can run all these things, you could potentially do that, right? So another one of our recent works was basically about trying to design scaffolding attacks to hide classifiers' dependence on certain bad features. So essentially what you see here in this picture is that there is a biased classifier that we created, which was essentially completely using gender to make its decisions on in-sample data points, okay, on the data distribution. And then the attack, I'll talk about in a bit what the attack is, but once we do the attack, that is the explanation generated by Lime, and Lime completely thinks that we are using some loan rate feature as the main feature. So it's not even detecting that like gender is being used predominantly. Similar thing with SHAP. It's not able to detect that gender is being used predominantly. It's thinking some other innocent, innocuous feature is being used, right? So what did we do here? I'll explain the attack just in a bit, but essentially this attack is exploiting one intuition about the behavior of Lime and SHAP. So while we talked about perturbations in Lime, the initial version of Lime essentially does binary perturbations. What I mean by that is it kind of transforms the input feature space to something that is just binary. So every feature will just have a 1 or 0 value, and when it does a perturbation, it basically flips ones to zeros by choosing features randomly which have 1 values. Okay, so it just does the flipping of ones and zeros when it does perturbations. Now, in doing that, what happens is, if I were to, so this is actually the Compass data set. what we did is took the instances of the compass data set, did a PCA, projected them onto these 2 dimensions, first dimension of PCA on the x-axis, second dimension on the y-axis, and you can see the original compass instances in blue. Compass is a data set that people often use in this community for thinking about criminal justice tasks, for example, right? It has its fair share of issues, but nevertheless, it is a popular data set. So blue is the original instances from the data, and the red is the perturbations generated by Lyman Sharp. Okay, so the insight from this is a lot of the perturbed data points are actually out of distribution. So that is happening, and I think in fact this resonates with the question or discussion some of you were also mentioning. So why do I say this is because I can actually construct accurate classifiers that can nicely separate points that are perturbations from points that are in the data. So those are separable, right? So those are in some sense distinctly sort of perceivable, at least by models, okay? So because of that, the intuition here is that adversaries can sort of exploit this notion or intuition and build a classifier that is highly biased on in-sample data points and is unbiased on out-of-distribution samples, right? So if I just create a classifier which is using race or gender through and through on the in-sample points and is using loan rate and income and other, legit features on the out-of-sample perturbations, then the fact that these approaches rely so heavily on perturbations means they'll not be able to see what is happening in sample. They'll just assume that the model is just doing whatever it is doing on out-of-sample perturbations, right? So that is basically the attack or the intuition behind it. So essentially, you can think of the setting as adversaries want to deploy some biased classifier in real world. Example, this classifier will just use race to make decisions. So adversary must provide black box access to customers and regulators who may use post hoc techniques like LIME or SHAP. As mandated by GDPR, they need to provide that query access. So the goal of adversary is to fool post hoc explanation techniques and hide the underlying biases of these models, right? So to that end, essentially the adversary can create this kind of a classifier where if the point is in the distribution, the adversarial classifier will return the label of the biased classifier. If the point is not in the distribution, which is out of distribution perturbation, the adversarial classifier will return the output of an unbiased classifier which uses the legitimate features, right? So that kind of scaffolding attack can already fool a lot of these kinds of algorithms, okay? All right, okay, so we discussed this, okay. So another thing that we slightly touched upon is there were also studies which kind of showed that explanations can be highly sensitive to random hyperparameters, including random seeds, right? So we went through some of the number of perturbations and so on, but random seeds and even that kind of patch sizes and so on, those hyperparameters are also going to influence the kinds of explanations you generate, and it's important to keep that in mind as we think about this. But by the way, just to also not make it super scandalous, these kinds of things are probably true with a lot of things we do in machine learning. Okay, that hasn't really stopped us from doing that anyway. So there is no sort of villain here in post hoc explanations. I think this is just how the field is going and sort of moving forward. Whether it's perfect, not really, but that's the status quo. It's not specific to explainability. I just want to say that. Okay. So this is one of our other studies that's actually hinting at what some of you were pointing out, which is so there is a way in which we as machine learning researchers think of what an explanation means and what a domain expert, let's say in healthcare or law, can think of explanations to mean, right? So for example, what we did was like this kind of a simple online user study with a bunch of law school students at Harvard. The task was, sort of bail adjudication, which is there is a classifier that basically is predicting if somebody is risky enough to be released on bail, so whether they're risky or not. And what we did was, so this is the classifier. So this is the true classifier. It relies on race. and it's clearly discriminating. This is a very bad classifier. And we constructed a high fidelity misleading global explanation for this. So essentially what we did was ensure that all the features like race and gender be removed when we construct that explanation. So if you guys recall, so we were constructing global explanations using rules earlier, and that's an explanation constructed using one of those approaches. It'll approximate this very accurately. So if you take the prediction match, whatever predictions that makes accurately match with the predictions made by this, but if you see it is relying on different features, right? So what we did was essentially take a bunch of law school students, assign some of them to see this true classifier, assign some of them to see that explanation, and then ask them the question of if this is what your classifier is doing, or I guess the more precise question was, if here is an explanation generated by state-of-the-art method for the underlying model, would you trust this enough to deploy or at least consider deploying this kind of a model? So unsurprisingly, if you show this model, most of them were like, nope, this is bad. It's using race, it's using gender, it's not, it's a no-go, right? But if we show that, they're like, oh, okay, so it seems to be using reasonable features. I use prior FTA, I use prior arrest, I use the criminal status of the person. So it's using all the features that I would use. So yeah, why not? Like, I mean, I'll at least consider deploying it, right? So this is again sort of the gap between they're assuming that an explanation will sort of be causal in some sense, right? At least with respect to the model, but that's not how all explanations are constructed, right? So that is the problem. So in fact, people are likely to trust that the underlying model with that explanation 10 times more than an underlying model with this explanation. So, okay. And there are also a bunch of other studies which basically demonstrate that post hoc explanations can instill overtrust. So for example, there is a nice study done by Microsoft Research and Harmanpreet Kaur. So they showed that domain experts and end users, first of all, they are not entirely understanding what these explanations are doing. And second of all, whenever there is explanation, they're kind of over-trusting the underlying model, no matter what the explanation is, right? So in some sense, they actually did these interviews with data scientists, and there are several interesting quotes, but essentially what they sort of infer from their studies that participations are trusting their tools because of their fancy visualizations and their well-documented GitHub packages, to put it very bluntly, right? So here are some quotes from that study. I think, let me see, which is a good one. So yeah, this, for example, this last one, the tool shows visualization of ML models, which is not something anything else I've worked with has done. It's very transparent, and that's why I trust it more, right? So I think, again, there is a big gap between how I think the research community is thinking about interpretability and how practitioners, even data scientists, you don't have to go to doctors or judges or lawyers, like even data scientists are not fully on board with what these approaches are doing, and there is a huge risk that they're over-trusting some of these things. Okay. All right. So I think maybe I'll cover this part a bit and then we can go for a break. So then there is the question of utility, right? So a lot of times when we are motivating, whether it's interpretations or explanations, we are basically saying that, oh, these are useful for debugging, for instance. So one of the study done with a housing price prediction task basically demonstrates that Amazon Mechanical Turkers are unable to really use linear model coefficients to capture or diagnose the mistakes that the model is making, right? But then you could argue that it's a very general population, they may not even interpret these coefficients or model well, which is reasonable, but like this is a finding, right? And similarly, I think there is another paper that came out in 2020 which showed that in a particular animal breed classification task, users familiar with machine learning are relying on labels instead of saliency maps for diagnosing model errors, right? But that said, there is one thing which I would hint to take with a pinch of salt. So the evidence at this point is really mixed. So in some cases, we are seeing that these, whether it's model interpretations or explanations, are adding value and they are improving something about the decision-making processes. In some cases, we are seeing contrary evidence, right? So I think that's why I was also highlighting to one of our prior questions that I think there is a need for like a clearer characterization. There is a need for more standardized experimentation and benchmarking so that at least, we understand that, okay, if I use these settings, if I do this exactly, this is the result that I would get, right? Or under these conditions, these are the results that I would get. I think that understanding currently is not there. It's of course an evolving field. So we are still trying to figure out what are the best practices, how to go about these things. But currently the evidence in favor or against these approaches are kind of mixed, right? So I think I'll pause here and then we can continue this discussion at 3 p.m. Does that sound good? Okay, thank you guys. Good. All right. Okay, all right. Welcome back, everyone. So this is our last hour or last part of this session. Thanks for sticking since morning. So I think we're almost at the tail end of it. So let's kind of jump back to what we were discussing right when we took the break. So we were talking about utility and, thinking about how post hoc explanations are being used in practice, like what are people finding and so on, right? So this is again some of like the very recent work out in 2022 by some of students in our group. So the idea here is to basically sort of think about, I think at an abstract level, we are all able to see that different post hoc explanation methods are generating potentially different looking explanations, right? So what are the implications of that? Like, are people able to understand that there are these differences and perceive them appropriately, right? So what we did here was essentially a bunch of like studies with practitioners, data scientists this time, working in some of the tech startups which actually focus on explainability. So there is like a direct connection in terms of these people sort of using these tools in a very regular basis. Okay. We did a bunch of semi-structured interviews, like 30-minute semi-structured interviews with about 25 data scientists. And several of them, like precisely 84% of them, actually said that they encountered disagreement between the explanations output by these methods almost on a consistent basis. What's also interesting is they actually say that they typically run not just one but multiple methods when they have to try to understand what are the features or what is the explanation of the model behavior for a particular prediction. Okay. So how are they thinking about disagreement? Because we are saying, okay, these explanations all look different, there's something different about them, but can we precisely characterize disagreement? And according to these people, here is how they think about disagreement, right? And this also boils down to some of the faithfulness metrics that we saw initially when we talked about if there is ground truth, feature importances of the model, right? So according to these people, they think two explanations are disagreeing if the top features in the explanation are different. So if I ask for a top K feature list and two explanation methods are giving me different answers, they consider that a disagreement. And the ordering among the top features is different. And the direction, which is the positive or negative side of contribution of these top features, is different, or even the relative ordering of certain features of interest is different, right? So now they're saying, yeah, we see a lot of differences. This is how we think of a difference. This is how we think two explanations would qualify as being different, right? So what do they do to resolve these disagreements? So if you run two methods, you see different answers, what do you do, right? The answer is actually not so optimistic one or a positive one. So what we did was a study to actually see how they're breaking the ties or what they do to proceed from this scenario of disagreement. Okay, so we showed these users explanations that disagree according to their own definitions of disagreement and asked them to make a choice as to which explanation they would pick and why. Okay, so they're choosing methods due to the following factors: associated theory or publication time, So if a paper has more theory in the method that it is proposing, for some reason that becomes more authentic or correct or authoritative than the other, or if it's more recently published, then that's more likely to be correct, or if the explanations match your own intuition better of what the model should do, then they're potentially picking such explanations. Or, types of data. For example, if it's tabular data, I'll probably use Lime and Chapin, not gradient-based methods, right? So here are some quotes, and as you can see, the factors that we just talked about are sort of sprinkled across these quotes, and you will, see them because it says Chap is a more rigorous approach than Lime, as it has theory, or in theory at least, right? So things like that. But the aspect of, maybe we should evaluate the faithfulness of these two explanations and compare them somehow. Or what about stability or fairness? So those are not cropping up as the things that they would do to pick one explanation over the other, and that is concerning, right? So in some sense, there are gaps between how research in these areas is progressing versus like how practitioners are taking all these tools and trying to do something with them in their day-to-day work. And sort of, it's kind of, we are bordering on all these kinds of issues which are clearly undesirable, right? So that's yet another sort of cautionary tale to sort of bridge the gap between research that is happening and also the practitioner community. Okay? So in summary, what we have seen is that a lot of these empirical studies or analysis are showing that some explanation methods do not reflect or faithfully capture the behavior of the underlying model. Some of these explanation methods can be easily manipulated. Slight changes to inputs can cause large changes in explanation, particularly for methods that use perturbations like Lime. Their utility in practice is something that we still need to sort of think more about, right? So that's one part of it. And on we are talking a lot about explanation methods or post hoc explanation methods. In fact, if you recall, we also saw that attention weights, which falls under our inherently interpretable models category, those are also not corresponding to meaningful information. That was another result that we saw, right? And there are no studies on prototype layers and adding them to sort of this whole deep learning pipelines, okay? And so which means, at least here, exploration is being done, so we know there are issues. So there are areas where there is not even exploration being done, and of course that we'll talk about that a bit more in future research problems. Okay? All right, so let's take a look at some of the theoretical results, both for the analysis of interpretable models, inherently interpretable models, and post hoc explanations, right? When it comes to inherently interpretable models, you'll potentially see you'll predominantly see two main classes of theoretical results. The first one is, it's basically about certifying the optimality of the lists or sets that are learned using certain procedures, right? So if I use my algorithm and generate such a rule list or such a rule set, I can certify that it will be within this much of the optimal. So that is one set of theoretical results you'll see. And there are also some more recent sort of results on saying that there are no accuracy interpretability trade-offs in certain settings. That means you can come up with an interpretable model which is simple enough, and it will also be the most accurate model. But while this is a good starting point, these settings are rather restrictive. For example, it's like RL with small mazes, right? So in such a setting, people have shown that there are no trade-offs, but that's clearly not representative of a lot of real-world settings. So while there are preliminary results, I think there is scope to do a lot more in these. Okay. Now let's talk about the theoretical results on the post hoc explanation method side. So this is one of the papers that I think kicked off the theoretical analysis of post hoc explanation methods by Gary et al. They did this analysis of a variant of Lime called tabular Lime, which only operates on discrete features and not on continuous features. So what they show is that they obtain closed form solutions of the average coefficients output by Lime, okay, when the underlying black box is a linear model. So all these results are just when the underlying model itself is a linear model, okay? And they also show that the coefficients obtained are proportional to the gradient of the function to be explained, again with respect to a linear model. And they show that the local error of the surrogate model is, bounded away from 0 with a high probability, right? So, the explanation's error is like bounded away from 0 with a high probability, okay? All right. So this is some of our work on unifying some of these methods, which is specifically Lime and smooth-grad. What we consider is actually a continuous version of Lime, where the perturbations are happening in a continuous space and not in a binary space or a discrete space. And we show that these two methods actually converge or output the same explanation in expectation. So if we basically have the ability to generate infinite number of perturbations and get an explanation, then the resulting explanation would sort of converge between these methods. Okay, but it's not that pessimistic. We can actually get it with finite samples as well. There is also that result. What we also show is that in expectation, the resulting explanations are provably robust according to the notion of Lipschitz continuity. So essentially, you can give some guarantees on the stability or robustness of these explanations in expectation. And we also have finite sample complexity bounds for the number of perturbed samples or perturbations required for these two methods to converge to their expected output. So what is the minimum number of samples M required for these two methods to converge to an output, result in the same output? So what would that look like, right? So another one of the recent works that we have been involved with, and I'm super excited about this one specifically, is to sort of bring some order to a lot of these post hoc explanation methods that are out there, right? So in a very, very recent paper, what we show is that various feature attribution methods, and when I use that word feature attribution methods, it is methods like Lime, continuous variant of Lime, SHAP, and all the gradient-based methods, they all generate some form of feature importance or feature attribution, right? So we show that these are all essentially local linear function approximations. So they're all trying to do a local linear function approximation, but the reason they all disagree with each other, as we have been seeing quite a bit in the past hour or so, is because they adopt different loss functions and different definitions of local neighborhoods. And this is precisely the different definitions of local neighborhoods and loss functions that they adopt. So this is at least trying to put some order as to they're all sort of unified in some ways, but at the same time there are differences because they're all adopting their own definition of what loss function to use and then how to define a local neighborhood, right? So we also have something called as a no free lunch theorem for explanation methods. Given that these methods all adopt a particular definition of what a local neighborhood looks like, no single method can perform optimally across all neighborhoods because they're all tailored towards certain definitions of what a local neighborhood should be, right? So this theorem is basically, to me, it's interesting, and also I think it has more implications, is that every time a new paper comes out, people show the performance that, oh, this beats it on everything else, right? So this result basically shows that no single method is going to work across all definitions of what a local neighborhood is, right? So that claim that this method beats everything, at least with respect to, certain aspects of it will not hold because of this theoretical result, okay? So with that, we are at the end of this module, and then we are going to discuss more about open problems, future research directions in the next 40 minutes or 45 minutes.